I've been teaching at Central for 23 years now, I guess, and if there's one thing I've learned about teaching is there's no such thing, I'm not going to teach you anything. Teaching is a selfing process. You, hopefully, my goal tonight is just to share my enthusiasm, share a little bit of knowledge, give you a foundation that will allow you to appreciate these amazing creatures we call herps, reptiles and amphibians. And then I'd really like you to realize if you want to learn about them, stay curious and get you a field guide. These two books, they're not that expensive, and if you can't afford to buy one, then you can talk to Mary. There might be some extras. You can check them. The library should have these. A good field guide is the best way to learn, and some curiosity is the best way to learn about the native creatures in your backyards. But we'll get you started, and so I don't want to waste any more time. So I want to jump into things. We're gonna discuss a little bit of background of what makes herps so special, and I might talk a little bit about their evolution, just so we can appreciate them, and we'll intersperse it with some meeting some of the herps in person. I brought all of the native creatures that I could find, and we have a live animal collection at Central that we use for teaching and education. But then I brought a few of my favorite non-native species, like Gila monsters and a boa constrictor, just so you can see how cool reptiles are. And if you are afraid, or if you have a thing where you don't like snakes, there's no pressure, but we do have, I brought a few rubber boas, and rubber boas are the best snake to meet if you want to get over a fear of snakes. So welcome to the wonderful world of herpetology. A couple of people mentioned that they are interested in frogs, so I'm going to bring back some sound and see. Recognize that sound? In a few weeks, you're going to start hearing it. We already have lost one amphibian species that was incredibly common, native here to Washington. The leopard frog was gone in Washington. Leopard frogs disappeared, I don't know, within the last decade. You guys might know.
They're technically still here, but they're limited to just a couple of spots down in the basement.
Yeah.
And they're definitely in prison.
In 1998, not long after I had a grad student, we did some work on the frogs near potholes. And they were common. We heard them. You could hear them calling at night, leopard frogs. And they've almost disappeared. You've probably heard about the extinction crisis. We'll talk about that a little bit. But amphibians have been hit particularly hard. It sounds like we have an expert on chytrid who did some research on chytrid fungus, which has taken out a lot of amphibians. And so we sort of take for granted this sound. These are our native Pacific chorus frogs. People call them tree frogs. They're in the family of tree frogs, but they're really chorus frogs. I mean, listen, they have a voice. And has anyone been out in the spring near a pond where it's almost deafening? You hear these. It's just amazing. So enjoy it this spring, and enjoy it whenever you hear it, because let's hope this never happens. But we may not have these creatures around forever, and if we don't take an interest in them and try to understand how we can keep them around. So that's part of the here. So that's our native Pacific chorus frog, and I actually brought one to show you. Right here. So this is in the Hylidae family, the family of tree frogs, and we're going to talk a little bit about evolution. Names are always changing. What's one thing really cool about being a biologist these days, and also extremely frustrating, is that as we learn more and more, as we have tools in molecular biology to help us understand evolutionary relationships of creatures, we're realizing their relationships change, that they're different than we thought. And so when people first thought maybe these frogs were really tree frogs, or they're chorus frogs, the scientific names are changing a lot. So you might notice a little confusion in the literature. Some people call this Hyla regilla, some people call it Pseudacris. Now there's a new Hyela, a new genus that they think it fits in with better. And that doesn't necessarily mean that scientists are confused. It just means that as we learn more, as we have better tools to understand relationships, evolutionary relationships, then the names get changed. But it's a Pacific chorus frog, and maybe I can ask one of my awesome colleagues to just, if you don't mind, just show people the frog, the chorus frog. And you can come up and look at it. We'll take some time. Is my voice loud enough, or would you prefer I use the mic?
Dan, do you want me to hold it or carry the...
Just carry it around so people can see it, please. Mike?
Hello? Well, I do have to hold it.
Yeah.
Otherwise, you saw what happened.
And especially when the air comes on.
Yeah, okay, so I'll use the mic. So they're amazing. And so why should we care about reptiles and amphibians? Well, we're in the midst of a sixth extinction. Most of us are probably familiar with this, but we are losing species on our planet at a rate faster than has happened since the Cretaceous extinction, when the dinosaurs disappeared about 65 million years ago. And the extinction we're experiencing now is brought about by us. It's just beginning. It doesn't have to become a mass extinction. We actually have it in our power to prevent the sixth extinction. And as I mentioned, reptiles and amphibians are a big part of that, especially amphibians. 1/3 of the amphibians in the world are threatened or endangered, and reptiles are not far behind. They're vulnerable creatures. And a lot of people have strong feelings about reptiles and amphibians. And that term herp comes from the Greek for creepy crawly thing, and they give people get the EBGBs from them, and that's usually because what we don't know we fear. Ignorance creates fear, and as we get to learn something about them, knowledge creates respect, and sometimes it can blossom into full-blown fascination and love, which is what happened to me as a kid. I got to know them, and they're cool. Amphibians and reptiles do a lot more for our well-being and health than we realize. We'll talk some about the toxins. There's a toxin in the Tarica, the newt, the rough-skinned newt, that was instrumental in humans understanding how nerves work, how nerves function, because it blocks sodium channels in nerves. A lot of our understanding of physiology comes from toxins that were found, isolated from snake venoms and amphibian skins. Amphibians have to keep their skin moist to breathe, because they breathe through their skin, and to keep your skin moist, you need to have some protection against pathogens. So they have all kinds of amazing toxins in their skins. We've learned lots about physiology from them. Some of our most important drugs come from reptiles, reptile venoms. Like, does anyone know about the ACE inhibitor blood pressure medicine? Probably heard about ACE inhibitors. They were discovered from the venom of a pit viper, and the whole pathway, the renin-angiotensin pathway, how blood pressure is regulated, was figured out because of these venoms in snakes that drop blood pressure. Now they're like the major blood pressure drug. My favorite example is I'll show you Gila monster in a minute. There's a new drug, fairly new drug called Byetta. It's a diabetes drug that was discovered from the venom of a Gila monster. And it's one of the leading treatments for type 2 diabetes, which about 25 million Americans suffer from. And there's many, many examples, really cool examples of drugs that have been developed from the venom of reptiles and amphibians. So we can appreciate that. Sometimes those examples are nice, but we don't have to value reptiles and amphibians just for what they can do for us. That's kind of arrogant, but that's how we are, because that's how we survived. But they are cool, just in and of themselves, and that's my hope tonight is when you get to see some of these creatures. If you don't already think they're cool, you'll come away from here thinking they're pretty cool. People don't realize it, but amphibians and reptiles form a really important part of food webs in ecological systems, in ecological communities, ecosystems. And we'll talk a little bit about that when we talk about ectothermy. And then they have a lot. One of the things I'm really fascinated with reptiles and amphibians as a teacher, I've learned over the years that they're a gateway. I could call snakes the gateway drug to science, because especially kids, have strong feelings about snakes. Usually they like snakes. Usually it's when you get a little older you stop liking them. And our feelings about snakes go deep in our psyche. They're part of our evolutionary program. The limbic system in primates evolved alongside dangerous snakes. And so we have innate fears of snakes. But we also have innate appreciation for beauty in nature. And all that gets tangled up in this wonderful way in the field of herpetology. And so these creatures have a lot to teach us about beauty and fear. And they're ancient, and they're important, they're stunning, and beautiful, and they're really cool. So that's why we should care, to start with. So I wanted to start out with a little overview of the players, the herps here in our state, and just to share with you some resources. So we talked about these field guides, and everyone should own a reptile and an amphibian field guide. These are you can take a peek at these during a break. These are the ones for the Pacific Northwest. The best all-around field guide for Western North America is the Stebbins Field Guide. And then if you travel to other parts of the country, there's wonderful field guides. They keep getting better and better and better. So a book that you can have in your hands, stick in your backpack, is crucial for going out and learning about herpetology. But there are some amazing web resources before you go out in the field where you see that snake in your garden or where you see that lizard on a rock, you want to figure out what it is. Here in Washington, we have it pretty easy. We really don't have that many native species of reptiles and amphibians. Go to Arizona, go to Mexico, and it's like mind-boggling. So we have, there's 27 species of amphibians that are native to our region. Some of them aren't. Some of them are introduced. Actually, bullfrogs are introduced. And 28 species of reptiles. So altogether, what is that? Like 58 species. You can get down, there's what, 30 of us in the room. We all get to know each other fairly quickly. I mean, you can learn 58 species of amphibians or reptiles pretty easily. Now, lots of the amphibians, the salamanders, you're probably not going to encounter here in the Methow Valley, except that one on the upper right. Who knows what that salamander is? That's the one you've probably seen if you've seen one here. Long-toed salamander. See this toe? These long toes on the hind foot, especially that toe there. Long-toed salamander. Those are the ones you see that come out in the rain in the fall and in the spring, and you see them around the ponds, and they wander off out into the shrub steppe, and they overwinter on land underground. It's pretty cool. So the sources that I would encourage you to have handy on your computer, there are two favorite web pages. This one, this is the Washington Department of Fish and Wildlife. It's an awesome web page. I can click on this and see if it'll show up on Google. And so you can go here to the Washington Herp Atlas, and we can go down and look at all our salamanders. The torrent salamanders, these are the ones that live in streams. You have to go more to the west side to find the southwestern part of the state. Here's our long-toed salamander. It's here in the Methow. Northwestern salamanders are up in the forest. Tiger salamander, I have one to show you. It's found in the deserts. It's found probably Okanagan, right? Right here. Yeah, and the one I brought is from Quincy. I brought a rough-skinned newt to show you. These are, if you get up in the mountains, into the Cascades, they're common in ponds, wet areas. The lungless salamanders, let's see, I missed the giant salamanders here. Dicamptodon tenebrosus, the Pacific giant salamander, you can see that up. Probably Snoqualmie Pass is probably the best, easiest place to see them. I didn't bring one to show you, but we have pictures. They're pretty amazing. They're endemic here in the Pacific Northwest. And we can go down the lungless salamanders. These are amazing creatures. They don't have lungs. They breathe through their skin. And they're the closest ones you can find here, probably down Cleellum. You'll find largemouth salamanders. And Satina just up in Whatcom County, I'm sure. Lots of in there. So these are amazing group of salamanders that make the Northwest famous for salamanders for this group, the lungless salamanders. Columbia Gorge is a wonderful place to see most of these species. And these are just Washington species. The spadefoots, we have a spadefoot toad to show you here. I call them toads because they look like toads, they act like toads. And these guys burrow underground in the dry season and come out and sometimes only spend a few weeks on the surface in breeding ponds. We have a couple of species of true toads, western toads, woodhouses. Western toads are here, not far away. Woodhouse's toad is more down in the eastern part of the state. They like places with streams, especially. And then our tree frog, our Pacific tree frog or Pacific chorus frog. We just saw that. And then we have some frogs in the family Rhonidae. Some of our native bullfrogs are not native. These are introduced, and they're causing lots of problems. The decline of the leopard frog is partly a result of bullfrog introduction. But if you're out in the forest and you see a frog up in the Cascades, on this side of the mountains, it's most likely going to be a Cascades frog, Rana cascadi. And then we have down in the valleys on the east side of the mountains, we have spotted frogs, Rana ludiventris. Someone here, this guy, call me a spotted frog.
They're here too.
And they're here? They're here too? Yeah. And then the most amazing frog that we have that is famous around the world are the tailed frogs in the family Ascaphidae. Ascaphus, these frogs live in streams, fairly fast streams, and most anurans, most frogs, have external fertilization. So the male grasps the female in amplexus, and the female lays her eggs, and as the eggs come out of the water, the male deposits sperm on the eggs, and they're fertilized into beautiful egg masses. Well, the Ascaphus, the tailed frogs, they live in these fast streams, and if you put your eggs out in the water, they just get washed away, and there's no chance for the sperm to find the eggs. So males actually have a copulatory organ, it's a little tail. They're the only anurans, the only frogs that have internal fertilization, and they're here in the Pacific Northwest, a really ancient family, amazing group of creatures. I wish I had one to show you, but I've seen them up at Brush Creek, up along the Pacific Crest Trail, which isn't too far up the Methow.
Twist River's good spot.
Say again?
Twist River's good.
Twist River, okay, cool. Yeah, so you're going to get from Scott next week.
Julie will talk about
Julie, we'll talk about, yeah. So you'll get, I'm just going to brush over, give kind of an overview. And then the reptiles, I'm more of a reptile person. Most of my research has been on rattlesnakes, Gila monsters, turtles, those and lizards, all kinds of lizards. So we have a fair number of reptiles here in the Pacific Northwest. Two native species of inland turtles, painted turtles and pond turtles. A slider is an introduced species that are people's pets that they let go, the red-eared sliders. Here in our region, you'll find painted turtles. I mentioned there's 7 ponds here in the valley. We have lots of them in Ellensburg. And then the western pond turtles are rarer and endangered, and there's some native pond turtles in the Columbia Gorge and some on the west side around Puget Sound. And then the lizards. So I'm not going to go into detail with all these. I have pictures I can show you at some point, but just to introduce the players, here in the valley, side-blotched lizards certainly up in the shrub steppe. You see side-blotched lizards? You have to get closer to the river and vantage area. Fence lizards certainly you'll see. Pygmy shorthorn lizards in the shrub steppe, and Scopus graciosa is probably a little farther east. Sagebrush lizards, and the little lizard, if you're digging in the garden in the rocks in the spring, you see a little lizard that shoots into the crevices like a snake. That's a skink. So skinks are, I'm sure they're pretty common here. And then not far from here, there are northern alligator lizards in the forest shrub steppe interface. I brought a southern alligator lizard to show you. And this is an ancient family of lizards, the anguid lizards, that interestingly are responsible for hearing aids. It turns out alligator lizards have these huge inner ears, the cochlea of the ear. They have these giant hair cells that line the cochlea. And decades ago, scientists realized they're a great model organism for understanding hearing. And if you look at the research in hearing, most of the work that has been done, models for understanding how ears work, come from alligator lizards, believe it or not. So that's kind of cool. And I brought one to show you. They are related, they're the closest group of lizards related to Gila monsters and beeta lizards, my favorite lizards, which I brought to show you. And then a number of snakes. So lizards and snakes are in the same group, in the same order, the Squamata. They're not taxonomically distinct. Some lizards are like Gila monsters and alligator lizards are more closely related to snakes than they are to other lizards. So lizards and snakes are all related to each other. They're not two distinctive evolutionary groups. But several species of wonderful snakes, and I brought a few of those to show you. And hopefully you'll get a chance to go into more detail with these later on. And then, of course, the rattlesnake we have here is the terminology, the taxonomy has been updated. It's the northern Pacific rattlesnake, not the western rattlesnake, and it's Crowlus oreganus that we have here in Washington, and they are amazing. If we have time, I'll show you some slides of some of the research that John and I have done, but I probably won't have time, and so John can cover that in a couple of weeks. We won't want to miss that. And then one of the most ancient families of snakes, the Boidae, they're so ancient that they still have a pelvis. If you do an x-ray of a boa, you'll see a vestigial pelvis. And males still have vestigial hind limbs. The boa I brought is a female. There might be a male in there I could show you. And so we have a boa here in the Pacific Northwest, rubber boa, which is really, really cool. So those are the players. Those are the creatures that are not that hard to become familiar with. There aren't that many of them. They're accessible. They're a click away on a web page. They're in your field guides, and they're out in nature. And so if you can just adopt an attitude of curiosity when you see something, you can pick it up, unless it's a rattlesnake, and you can you can differentiate a rattlesnake from anything else, and you can look at it and you can figure out what it is. And if you can't, you can ask John or Scott or anyone who does. You consult your field guide. So that gets us started.
The Washington Herp Atlas is one of the main resources listed. If you haven't looked at that document yet, it's right there. And
yeah,
I encourage you to go, especially before each amphibian or reptile class, click on any of these and get a little.
Yeah, so let's say a long-toed salamander. We click on the long-toed salamander. There's some information, general description, identification tips. I really like these maps. You click on the distribution maps, and the maps show you actual localities, not just a fuzzy region, but actual localities, so you can see up where we are. Hey, there's lots of observations of long-toed salamanders, so you can get a feel for where these animals are found in the state. It's an awesome webpage. So I encourage you to play with it. Instead of going on Facebook, go here. Go look at these animals. It's way more productive. And the pictures of the animals on Facebook are at least as interesting as all those pictures of people on Facebook, So think about that. And then you can share them with your friends. So another good webpage here is the Burke Museum website. This one's got lots of beautiful pictures and good natural history information. Just want to show it to you. So you'll bookmark that one too and use it as a resource. Well, when it opens up, there we go. So that this one you can scroll down and it gives you all the salamanders and little natural history notes. If you want to learn more, let's say we want to learn something about, let's say let's find our Pacific tree frog. So we can click on that, and then we can learn more natural history about the tree frogs, some nice photos, or chorus frog. And it's a great website too. So there. So those are the players. And I'm not going to spend that much time talking about any one species, but we do have some for you to look at. So I think you're going to learn how to identify many of them just by the examples of some of the critters that we have. So before we do go any farther, though, let's just talk a little bit about another thing that makes these creatures so interesting is a little bit about their evolution. So the earliest amphibians go back 360 million years. That's a long time. There's actually a pretty decent fossil record. It keeps getting better and better. transition fossils from fish to amphibians. And the first recognizable amphibian, Ichthyostega, this guy here, shows up about 262 million years ago. And basically it's a gradual transition from a round head with eyes on the side to a flat head with eyes on the top and limbs that develop over time. And so amphibians show up. They're ancient. They're not as old as fish, but they're ancient, 360 million years. Not long after that, a major evolutionary breakthrough. So amphibians have what's called a cleidoic egg. Amphibian eggs have to be laid in water. They need water to keep the nutrients moving into the embryo. So amphibian eggs need to have water. A major evolutionary breakthrough that happened about 340 million years ago that allowed reptiles and mammals to evolve was the amniotic egg. And the amniotic egg has membranes that surround a food supply, a water supply, and a waste repository, like a garbage can, all put together in the egg.
Always fresh water? Are there any amphibians?
Those lump salamanders on the west side, they lay eggs fresh.
Okay, treasure, but none in salt water.
None in salt water. And some plethodonid salamanders can lay their eggs on the land, but they still need water. They're not a self-contained little package like the amniotic egg. Although it's really cool that some amphibians have found a way around that and have evolved and have a land and still make their eggs. But it's rare. Amphibians are at some stage in their life, they're tied to water. And this amniotic egg was a major evolutionary breakthrough. When the amniotic egg shows up in the fossil record, then reptiles and mammals radiate really fast. So the oldest known reptile dates back pretty far, 320 million years. And it was found in remains of fossilized club moss in Nova Scotia. This Hylonomus, this is the oldest known reptile. Lived in these club moss trunks, and the idea is it got down into these trunks and then got trapped and fossilized. So here's a sort of an overview of the evolutionary relationships of vertebrates. And there's a lot of stuff here, and some of you may know what all this means, and some of you may not. That it doesn't really matter too much. Except I'm just going to guide you through a few things to help us appreciate the place of amphibians and reptiles in vertebrate evolution. So here's our fish up here, and here's our oldest ancestor that dates back maybe more than 400 million years. And so we have these ancient fish, jawless fishes show up, and we have cartilaginous fish show up, and ray fin, bony fishes, and lungfish show up, and then, like I said, then the salamander, the amphibians show up. That's 360 million years ago. And those are tetrapods. So amphibians, reptiles, and mammals, tetrapods means they have tetra, four legs, four limbs. So these are the limbed creatures, the limbed vertebrates, or the tetrapods. And amphibians show up first, and then the amniotic egg comes along, so that's amniota. And then when the amniotic egg comes along, you get this radiation of reptiles and mammals, turtles, the tuatara and the lizards and snakes. These are called lepidosauurs. They're lizard-like creatures, and some don't have legs, they're snakes. And then crocodilians and birds are actually very closely related. So that's kind of starts to get a little crazy here when we get up into reptiles with birds, which are really reptiles. And we've learned this in the last couple of decades looking at their molecular biology especially, but birds are definitely reptiles. In fact, you probably all know, birds are dinosaurs. The dinosaurs did not go extinct in the Cretaceous. One major line of dinosaurs continued, and they're birds. And they're reptiles. They're also reptiles. They share this amniotic egg. And then we have the mammals over here, which have a lot more in common with reptiles, certainly, than reptiles have in common with amphibians. And mammals, you talked about this last year, of course, that they have mammary glands and hair, and some have scales, and reptiles have scales and some have feathers, and amphibians don't have any scales. So they did early in their evolutionary history. They have smooth skin, and they're very different. And so then we've got birds. So then we have this field of herpetology, right? So herpetology is reptiles and amphibians. Ornithology is just this one little group here, birds. Actually, they're a pretty big group. What are there, like, how many million species? Or 1,000 species of birds? 8,000, maybe 10,000, something. And then we have mammals down here, but why? Something's just doesn't make sense. Because we have the field of herpetology as reptiles and amphibians. Amphibians are probably more closely aligned with fish than they are with reptiles. So what's up with that? I mean, why do we lump them all in this one group? What's going on? Why? We got to find something to bring us together, to unite the field of herpetology, reptiles and amphibians. Somebody said, what is it? Yeah, that's what unites us, ectothermy. Ectothermy is what unites, what brings reptiles and amphibians together as a science. And of course, when the field of herpetology was invented or first started, I don't know, maybe the 16th century, 17th century, people didn't know evolutionary relationships, but they knew these critters that creeped and crawled, and they were ectotherms, they were cold-blooded. So let's talk about this a little bit, and it really is the key to understanding the natural history of amphibians and reptiles, is to understand a little bit about ectothermy. So here's some ectotherms, some of my favorite ones, Gila monsters, rattlesnakes. These are related to our Pacific tree frogs. These are canyon tree frogs. Someone wondered, how does a tree frog survive in such a dry place? So we're going to talk about this in a minute. And this is a toad that lives in the desert. It's not too distantly related to our toads that live in the forest. So let's talk about ectothermy. Ectothermy is a mode of temperature regulation where the body temperature is determined by the environment. Ecto, outside, body, therm, temperature. So the body temperature of ectotherms is determined largely by the organism's external environment. They pick up heat from the outside. So a Gila monster lays on or a lizard lays on a warm substrate, picks up heat from the sunshine. Endotherms derive their body temperature from inside, so do their own internal metabolism. So those are important terms, and related terms are, well, one related term is cold-blooded, which is the term, the vernacular used for ectothermy. But cold-blooded does not do them justice, because many ectotherms are very hot-blooded. Related terms are poikilothermy, where the body temperature fluctuates, and many ectotherms are also poikilotherms, but not all poikilotherms are necessarily ectotherms, because some birds and mammals can allow their body temperature to fluctuate. And then the other term is homeothermy, where the temperature remains constant. So these are maybe some of the terms you're familiar with, but really what I want you to come away with our discussion is this idea of ectothermy. Deriving your body temperature from your environment is hugely important for amphibians and reptiles. It defines who they are, and it allows them to live where they do and to do what they do. So let's talk a little more about why. So I'm going to nerd out here a little bit for just a second. So one thing that's really interesting about endotherms, birds and mammals, is to heat your body, that heat needs to come from your own metabolism. It takes a lot of energy. And endothermic tissues, liver, heart, and brain, they're more metabolically active in endotherms. They have more mitochondria in the cells. Mitochondria are the organelles in your cells that create ATP, and they also create heat. And so endotherm tissues are packed with these little powerhouses that create heat. And what goes on inside of the tissues in an endotherm is they decouple that when your ATP in your cells when your mitochondria make ATP, it can be really efficient in an ectotherm and release hardly any heat. But in an ectotherm, the membranes in our mitochondria are leaky in a sense, And a lot of extra heat is given off in the production of ATP. And that's where our heat comes from, at the cellular level. And it takes a lot of energy to create that heat that we need to keep our body temperature warm and keep us active when it might be cold outside. But that comes at a cost, because endotherms have to eat more. And ectotherms save a ton of energy by not having to maintain high and constant body temperature. So that's the key. And I'm sure, did everyone read that paper by Harvey Poe on the advantages of ectothermy? Did anyone read that paper? You looked at it? Yeah.
Could I ask you a question?
Yes.
Yeah, it said that it was an advantage to have a narrow range in body temperature, which I thought, and it was seeming to say that endotherms maybe don't have that, but I thought we were even narrower than the 10 degrees or whatever. I didn't understand, and why is that an advantage?
Well, I think the advantage is that range can be maintained behaviorally, but you have a choice of maintaining the range, and I've got some slides to show you about that. Or if you move outside of that range, like you allow yourself to get cold, your metabolic rate plummets and you save a lot of energy. So you only maintain that range of temperatures when the thermal environment allows you to, and you only do it when you have to. The rest of the time you can save a lot of energy. And when you do maintain your body temperature, it doesn't take nearly as much energy because you're deriving the heat from the environment rather than your own energy stores. So endotherms include birds and mammals. They have high metabolic rates. They need to maintain a constant body temperature. And ectotherms include our herps and fish. And then in general, the metabolic rate of, let's say, a rattlesnake versus a squirrel that weighs the same is less than 1/10. So a rattlesnake can get by on about less than 1/10 of the food that a squirrel can get by on. So that's pretty amazing. Low cost approach. Saves a lot of energy. So that gives ectotherms a huge advantage in energy efficiency over endotherms. And that's why in places that are low productivity, like deserts, where you may not find so many animals, you'll see more reptiles, especially reptiles, where it's dry. Because they can take that energy directly from the environment and maintain the body temperature. They don't need to eat as much. So let's keep following that logic. So here's a graph that shows the relationship between body mass and energy metabolism, and it just compares birds, mammals, placental mammals, and reptiles and amphibians. So for any given body mass, say at 10 grams, a lizard or an amphibian has, you can barely even see, maybe 5 joules per gram per hour, where a similar sized placental mammal is almost up to 50. So 10-fold difference. It's huge. Birds, it's even bigger. Birds have very high metabolic rates because their body temperatures are higher and they're tend to be more active and often smaller. So it's a huge energy savings for an ectotherm. So the metabolic heat is not required for thermoregulation. They get that from their environment. Their metabolic rate drops with the decrease in body temperature in cooler microenvironments. So when a rattlesnake goes down into its burrow at night, or a lizard goes into its shelter at night, metabolic rate drops, and when your body temperature drops, your metabolism slows. So they save even more energy. And they don't have to be active as much because they don't need as much food. And so they save energy there also. And this is a horn lizard. This is my student, Megan, who did her master's thesis on horn lizards a few years ago. So these guys can specialize on ants. And they can eat a meal of ants and go down and burrow and digest for a few days and come out again and have another meal of ants. They don't need to eat very often. And the Gila monster, okay, I'm going to get out. Gila monster is my favorite example. So let me show you this. So here's an example of what an ectotherm can do to regulate its body temperature. And so I got to pull out Chucho. You get to see the Gila monster. So John's going to show you Chucho. So this Gila monster, okay, here's my story with the dentist. This Gila monster came into the world because of this brilliant reptile breeder named Mark Seward. Mark Seward is famous for breeding Gila monsters. He's a dentist, and he financed all of his. He's got a huge reptile collection from being a dentist. He was a dentist for like 30 years, saved up a ton of money, and his real passion is breeding Gila monsters. And this was one of his lizards that was bred. Probably this lizard's a good 15 years old, and it's from southern Utah, Gila monsters, but it's a captive bred lizard that a student at Winthrop College had and donated it to Central a few years ago. So I thought that was cool. So yeah. So Gila monsters are venomous. They and the Mexican beetle lizard, I have one up here to show you, are the only venomous lizards. And their venom gland is in the lower jaw. I mentioned that the diabetes drug that discovered from their venom. It was actually Utah Gila monsters that discovery came from in the 80s. And I worked on them for my master's. I've done a lot of research on Gila monsters and beetle lizards over the years, my favorite animals. So don't stick your finger around his mouth. He's pretty mellow, and he's not going to bite anyone, but you don't want to tempt. Don't tempt him. Don't stick your hand near his mouth. Their venom is built to cause pain. It won't kill you, but if you were bitten by a Gila monster, you would think death would be preferred. Because it is one of the world's most painful toxins. It's built to cause pain because they can't move very fast. They're slow, and they don't run. They don't sprint. So if they weren't venomous to protect themselves, they would have gone extinct a long time ago. So this figure, the Gila monster is a lot more interesting than this figure. But if you look at this, there's a pointer, isn't there? Let's see. Does that have a laser on it? This is a laser. So this is Tiny. This was a Gila monster had a radio transmitter in him. I was tracking him. This is in southern Utah. Tiny might even be related to Chicho. Who knows? But so I'm tracking this Gila monster, and I've got a radio transmitter. I'm measuring his body temperature, and I've got all these thermocouples. And I'm measuring the temperature of his environment. And the shady region of the graph is when the Gila monster's in the shelter. And this white region is when he comes out of his shelter. So the red line is his body temperature. So in the morning he's in the shelter, his body temperature is dropping, kind of following the temperature inside the shelter, a little bit warmer maybe. This is air, and this is the surface of the ground. So Tiny comes out of his shelter about 9:30 in the morning, and here he comes out, and he warms up really fast, and then he goes back in, he cools down, he comes out, he warms up, and then through a period of a couple hours during the day, he's shuttling in and out of his shelter and maintaining a body temperature right around 30 degrees. That's about 86 degrees Fahrenheit. That's what the temperature they like. And that's when they like to go forage and feed and fight with other lizards and do their thing. And they notice it gets really hot here in the middle of the day. The substrate warms up, and then he goes into shelter here. His body temperature drops, and he comes back out again, basks a little bit in the afternoon, and he goes back into his shelter. And so that's kind of a typical day for a Gila monster in the spring. So he's behaviorally thermoregulating, keeping his body temperature where he needs it to be when the thermal environment will allow him to do that. And he doesn't use any energy to do that. All that energy comes from the sun and the ground. So behavioral thermoregulation is really important for ectotherms. And they're not necessarily cold-blooded. Cold-blooded is not a good term because if you've ever picked up a lizard when they're active in the desert, and these guys are the champions, these desert llamas, their body temperature will go up to 45 degrees centigrade, beyond 45 degrees centigrade, which is 116 degrees Fahrenheit. You pick up this lizard, if you can catch one, we use nooses. If you catch one, you hold it, it feels hot, very hot to the touch. That's one of the highest body temperatures tolerated by any vertebrate, and it's anything but cold-blooded. So cold-blooded is not a real good term for ectotherms. So here's a figure, and John and I are doing this now with some of the snakes here in the Methow. But this is Cooper the rattlesnake. This is a den near Ellensburg. And so what we do with the rattlesnakes to try to understand their thermal biology is we put these little data loggers, surgically implant them in the snake, and then we monitor them over the year with greater telemetry. And this data logger records body temperature every hour from the snake. And so we have a trace here of Cooper's body temperature for almost for a whole year, from mid-June of 2012 to May of 2013. And you can see during the summer when he's out foraging, his body temperature's bouncing around every day, up and down, up and down. He gets pretty cool at night. He gets down, even in the late summer, he gets down to below 5 degrees at night. It's pretty cold. And then, when do you think he goes into hibernation? You tell? Right about there. It's the second week of October. Down he goes. Gradually drops. So he's underground in a den all winter, about 6 months, and then boom, he comes out in April, and he's thermoregulating again, doing his thing. And so during this entire period, as his body temperature plummets, he's saving a ton of energy. As body temperature drops, their metabolic rate, for every 10 degrees drop in temperature, their metabolic rate drops about 3-fold. So they save a lot of energy. They basically go into a state of suspended animation in winter. So that saves a lot. So here, just to kind of summarize some of the consequences of being an ectotherm. They thermoregulate behaviorally, and so choosing the right habitat, temperature habitat, is really important for reptiles and amphibians. So when you're thinking about when you want to see rattlesnakes in the spring, or when you want to find fence lizards, you should think about temperature. And I always, whenever I go out, I always feel the ground and kind of, you get a feel for a good temperature, a diversity of temperatures where they can thermoregulate. If it gets too hot, then you're not going to see them. It'll be too hot, and they'll go underground. So it's always important to think about temperature when you're looking for reptiles and amphibians, or you're finding them, especially reptiles, because they thermoregulate more precisely than amphibians. Why do you think that is? Why can a reptile have the luxury of allowing its body temperature to fluctuate more, or to regulate its temperature if it needs to, than an amphibian?
Amphibians are water, right?
Yeah. Yeah, if an amphibian goes out to bask in the sun like these rattlesnakes, they're going to dry out. That can be a problem. Although, if they're along a creek and there's plenty of water, they will bask sometimes. Toads will bask. We've watched them. Tree frogs will bask. Tree frogs will warm way up, and then if they start to dry out, they go back into the water. So behavioral thermoregulation is beautiful. It's wonderful. You've probably seen them basking. They'll do, when they're doing their push-ups and things. That's related. It's not the same. And then ectothermy saves energy, so they have less than 1/10 of the metabolic rate of an endotherm. And at lower body temperatures, it's even lower. The Q10 means the drop in body temperature with a 10-degree drop in temperature, or drop in metabolic rate with a 10-degree drop in temperature. And so they don't need to be active as much, and that's why reptiles and amphibians tend to be more secretive. It's harder for predators to find them. They're at risk for predators. And they can also be smaller. We'll talk about this. You don't see any endotherms that are as tiny as a salamander or a sharp-tailed snake. So this opens up a whole new set of niches for ectotherms, terrestrial ectotherms. So frogs and salamanders and snakes can be much smaller than vertebrate endotherms like birds and mammals. Smallest mammal, a shrew. Smallest bird, a hummingbird. Smallest amphibian, salamanders weigh about 1/10 of a hummingbird. It's amazing. They can get really small. And their role in the trophic structure of ecological communities can be greater because, I'll talk about this in a sec, because they're so energy efficient, they convert energy faster, and they can get by on a smaller amount of food, can sustain a greater population of ectotherms. So let's talk about that. So, okay, so here's another native species for us to look at. These guys are, and you have them here, spadefoots. There's 2 in this container. So, any volunteers want to carry this around? Thank you. So, peek in here, and you'll see one of them on the surface, and then another one's buried itself. So let's talk about amphibian, how amphibians. So here we are with our Great Basin spadefoot. Spadefoots have this bony tubercle on their hind foot. It's like a little, that's why they call them a spadefoot. It's like a little shovel. And what they do is they get in sandy soil, and they just push soil on top of themselves with those spades. Their feet allow them to just go straight. They can dig straight down. And a friend of mine was studying how they overwinter, where they go, and he tied yarn to their feet to see how deep they could go, and he marked it. And they can go a meter deep into the sand in the basin. They will go a meter down below the surface, and they can last for 3 years. I'm not sure about our species here in Washington, but this was in Arizona, in Yuma, Arizona. This is a different species. This is Couchy spadefoot. They can last 3 years underground, just chilling, because they store energy. They have really low metabolic rate. Another really cool thing is the toads, the spadefoots, as they sort of follow the water table as they go down, the moisture in the soil, like roots of a plant. They just go down deeper and deeper and deeper, and they absorb, because amphibians, we'll talk about this in a minute, amphibians have leaky skins, right? I mean, that's how they breathe. Many of them breathe through their skin, so their skin has to stay moist, and they lose water really fast. But that also allows them to gain water through their skin, and so they can draw water in from their environment as they dig down into the sand. And the desert can be bone dry on the surface, but if they're down even a few centimeters, or certainly a meter below the surface, they're pulling water into the body. And as they dry out over those 3 years, as their tissues start to get dry, they concentrate urea in their cells, and urea is a salt that's osmotically active, and they pull water in even better. It's like a sponge sucking water from the environment. And then when the rains come, they'll come out and feed. And some of the southwestern spadefoots can spend maybe a week on the surface feeding, breeding, and they go back down under, and they might last for another year underground. So they're the champions of little activity. Our spadefoots here in Washington are more active because there's more water available to them. But in dry years, they can disappear entirely for a whole year, and you won't see them when they come back. It's pretty amazing. So check out these little guys. We put some sand in the bucket there. You can see how they are digging down. So then ectothermian body size. So again, birds and mammals, especially mammals, most mammals weigh over 20 grams, but over 80% of lizards and 90% of amphibians weigh under 20 grams. Many weigh less. So here's a sharp-tailed snake. Has anyone seen a sharp-tailed snake? We have them not far. Well, yeah, I can see them.
In Yakima.
In Yakima.
Some lady brought these things in and said, our cat has been catching these. What are they?
And you knew what they were.
No, I had to find out, and we took them up to Central, and their colleagues were totally excited.
Oh, they're so cool. Yeah, Cleella, we have them in Ellensburg. Coverboards. If you want to find snakes, especially in your yards or your van, or amphibians too, put down little 3/4 inch plywood works best. Just scraps of plywood. Great place to. We call them coverboards, and in the springtime you can lift them up. I have them scattered all over on our van, except my wife's moving them, and I always put them back. But we get gopher snakes and rubber boas and racers and garter snakes under these coverboards, and sometimes sharp-tailed snakes. So look at that. That's a juvenile, but there's Penny. So these are one of the smallest snakes in the world. It's our Contia tenuis, our sharp-tailed snake, and these are found here in Washington. And here's a juvenile Insatina, and that's a person's finger. So these are tiny. So how can they get so small? Or why is it that birds and mammals can't get quite so small? What's up with that?
Muscle mass being required for the endotherm?
Yeah, okay, keep going with that. Yeah, they need bigger to hold enough food. Keep going.
Surface area to volume.
Say it louder.
Surface area to volume.
Yeah, there it is. Surface area to volume. The smaller you get, the more surface area you have exposed to the environment, the more work it is to maintain homeostasis. The more energy it takes. But if you don't need much energy anyway, if you're an ectotherm, you can afford to get really small before you reach that threshold where you can't maintain homeostasis anymore. And so you get snakes. I mean, you can get these tiny snakes. Down where we work in Mexico, there's a whole guild of these little tiny snakes. They're called thread snakes. It's amazing how small an ectotherm can get, and that opens up a set of niches that birds and mammals can't get to. So these little sharp-tailed snakes feed on slugs, and some of these salamanders feed on little tiny, even flatworm, roundworm-sized creatures in the soil. They feed on really tiny things that birds and mammals can't waste their time on. And then they convert them into salamander biomass or snake biomass, and they become a food source to the next trophic level, and they create a part of the food web that it would not be available otherwise if there weren't these cool vertebrate ectotherms. So they're a really important part of our food webs that we don't recognize very often. And here's a bunch of numbers just to show you. These are ecological efficiencies. So what this is when an animal eats its food, a certain amount of that energy that's taken into the food is used for maintenance, and then it has a certain amount to give to offspring. And so the ecological efficiency, so this number 48 for the redback salamander, that means for every calorie, or for every, that's 48% of the energy that this animal takes in is put into offspring. So for every gram of food, then 0.48 grams can be converted to offspring. And look how efficient ectotherms are, 76. Some of them are like into the 90s. Some Desmognathus salamanders, like 90% of the energy they take in is converted to new salamanders, to eggs and new salamanders. But if you look at endotherms, birds and mammals, maybe 1%, 2%, humans, probably 0.5%. Most of our energy goes to maintaining our body temperature and everything else. And we have very little left over to give to the next trophic level, to going up the food chain. So this is really important. And some scientists did some research in New Hampshire at Hubbard Brook. This could be done here in the Pacific Northwest. It'd be really cool. And they looked at the salamander community, and this is a species of salamander, the redback, the Desmognathus eastern redback salamander, or Plethodon cinereus. We have Plethodon vehiculum here in the Pacific Northwest. It's very similar. The salamander weighs about 1 gram, and these scientists did this, measured all these parameters in the forest, and they found that the salamander community consumed about 46,000 kilojoules. So those are related to calories, whereas all the birds ate quite a bit more than the salamanders. So you might think, well, the salamanders don't have much of an impact on the community because the birds are eating a lot more food than the salamanders. But then when you look at the efficiency that the salamanders turn that food into new salamanders, they were more than 10 times as efficient as the birds. And so for every gram of food eaten, there's way more salamanders added to the next trophic level. Beyond birds, beyond mammals, beyond any of the endotherms. And so when a predator's out there in the forest and it's looking for food, there are ectotherms to eat. And so they are a really important part of our food web, and including rattlesnakes, where we live. So let's just talk about rattlesnakes a little bit because they're really cool. So this is a photograph that John took. You sent that to me.
Right, I didn't take it. Somebody took that on the Monument Creek Trail.
Okay. So there's a northern Pacific rattlesnake eating a cottontail rabbit. That rabbit, and part of my PhD work was looking at metabolic rates of snakes. So I can tell you that rabbit probably has enough energy to sustain that snake for a whole year. They basically need to eat about equivalent to their body mass per year to survive. So one good meal will last that snake a year. And now if it's growing and reproducing, maybe it'll need to eat a little bit more. This is a black-tailed rattlesnake that's digesting a pack rat and just putting the part of its body with the food bolus in its sun. Keeping away from predators, but still thermoregulating. So that was pretty cool. So let's contrast the rattlesnake with an urban, a weasel. And weasels, they're about the same mass, roughly. And weasels love these voles. And a weasel has to eat a couple of voles a day to survive. So over the course of a year, A weasel will need to eat hundreds of voles. A rattlesnake, to survive over a year, can pretty easily get by from 6 to 12 voles a year. So less than a tenth of what this endothermic predator, ectothermic predator. So when you go out the trophic level, then what would sustain a couple of weasels for a year, you could sustain about 40 to 60 rattlesnakes. And because of that, these rattlesnakes are available to the next trophic level, and all of our other, especially avian predators like red-tailed hawks, feed into this. So they enrich the system just from energy alone, not to mention the other ways as predators. So that's all I got to say about ectothermy. I do want to talk a little bit about amphibians.
Can I ask you one question?
Yeah, please.
So, in layman's terms, could you sum up the molecular difference? Like you're just talking about the weasel and the rattlesnake. So is the difference molecularly that for the rattlesnakes, he's not converting any of that rabbit into body heat because did it have something to do with like heat leaking out of the cell membrane?
Yeah, so what it has to do with is in our cells, all of our cells, we have mitochondria that produce ATP that we use for our immediate source of energy to move and to do everything. Mammals in their mitochondria, rather than just making ATP, the biochemical conversion of ATP is not as efficient. Basically, the membranes are leakier, and so instead of making ATP, they create heat, and which is good for us because we need that heat. And so all of our tissues are just running at a higher idle speed, producing more heat, and they're not as efficient at producing ATP that we need for our basic energy needs. Ectotherms, on the other hand, are very efficient.
We're not as advanced as reptiles?
No, we're not, totally not. They're way ahead of us. And okay, along those same lines, the hearts of reptiles and amphibians are amazing. So you'll hear people say, oh, well, birds and mammals have these more evolved hearts, 4-chambered hearts that don't allow deoxygenated and oxygenated blood to intermix. Ectotherms, well, at least most all reptiles except crocodilians, because they're birds. And amphibians have 3-chambered hearts, and they either can or cannot allow the oxygenated and deoxygenated blood to intermix. But if you're a salamander, you don't have lungs. Well, you don't want to waste an extra chamber in your heart sending blood to the lungs. So their hearts are incredibly versatile. They can either keep the oxygenated, deoxygenated blood from intermixing, or they can mix them together if their energy demands aren't really high. And you start looking into it, and you really realize how exquisitely adapted they are for those low energy lifestyles. So they're not primitive at all. So, thanks, John. That's a great question. Are there some other questions before I wanted to talk a little bit about amphibian biology?
So in the ectothermic animals, they must have a whole different set of enzymes that run their body, because in mammals and birds, our enzymes are highly temperature dependent.
Yeah, great question. They do. They have, well, their enzymes are similar, but they're little slightly different versions of our enzymes that function at different temperatures. And they still have thermal optima. So a Gila monster, for example, or a rattlesnake, they'll thermoregulate right around 30 degrees, and that's the temperature where they digest best and they move best, and they can do their stuff. So their enzymes still evolve that thermal optimum, but they don't have to stay in that range all the time, and so they can cool down and save energy at other times. But they do have, it's a whole different suite of enzymes. Or even like fish that live in 7-degree or colder water, they have their enzymes are all built to function at low temperatures. Yeah, it's fascinating.
What are some of the predators of the Gila monster that's at this poison?
Yeah, that's a good question. Well, roadrunners are brutal on young ones. Once a full-size Gila monster, once they get to be adult-sized, almost nothing messes with them. But as they grow, as they're smaller, coyotes, kit fox, bobcats, mountain lions even. Mountain lions won't even adult. So, but that skin is so tough. They're so, an adult Gila monster, I've seen coyotes grab them and shake them and move them, you know, like you'd think the Gila monster would be dead. It doesn't. It hardly even hurts them. They're so tough. Those osteoderms are very protective. Yeah.
So per gram of food, they can put more of that energy towards reproduction, but they also eat a lot less food because they have lower needs. So
Correct.
What's productivity like in the end?
Well, so if it doesn't take as much food, you can sustain a population of rattlesnakes on a lot fewer voles.
But are they
Then you could-
productive in a way that like utilizes that? I mean,
Yeah, they use it. They just get by on less.
but in terms of like their rate of producing young, like their
They can-
like biological productivity.
Yeah, so their fecundity. So a rattlesnake depends. You know, species vary a lot, but they can have just as many offspring. They can produce more offspring on less food. So I think what you're saying is, well, they're just slow. Everything happens slower and less. So is that what you're asking?
Yeah, I was just
Sort of.
curious. They're more efficient, but they eat a lot less, and so they would
Correct.
theoretically have less to put.
They won't have as. They'll have more. They eat for the same amount of food. They can put more into the next trophic level. But a population of 100 rattlesnakes will have far less of an impact on its prey base than a population of 100 weasels. Yeah. So, but
They don't necessarily limit what they eat though, because I rarely kill a snake, but one of the rattlesnakes that I did have to kill had 5 mice in it.
yeah, well, he just eaten a good meal.
Yeah.
So
very good meal.
after a meal like that, you know, they'll go and digest, and they probably won't eat for a very long time. They do limit it in the sense that if they have enough energy, if they have enough food, why risk being killed by a human or another predator if you can go high, or you can do something else. So
Yeah.
that's a lot of the way that their lifestyle works.
So, I have a question about when, like, sometimes you see a snake try to eat something that's way too big for it, like I'm watching this garter snake try to eat this fish, and like, it's just sitting there forever, it's like, and so it's really exposing itself to being picked off.
Yeah.
So, is there some kind of like, way that, I've just been surprised
Yeah,
at
it's
how they,
amazing.
it just seems like, that's dumb, why are you going for that? Like,
Yeah.
you're just sitting out there, you're gonna most likely get picked off, and like evolutionarily, like,
Doesn't make
did you
any
figure it
sense.
out that you don't go for things, and you don't need that much anyway, so like, so why bother?
Yeah. That's a great question. I don't know how to answer that question. I
Or
could
even
come up with
like the five,
speculative.
like, why five mice? Like, if it ain't
Yeah.
5 mice, you're gonna be so heavy and weighed down, it's way more than you need forever and ever.
Well, but if you find them, they're hard to find and they're hard to subdue. And if you have 5 mice and you eat 5 mice, that's going to be the whole year. So go for it if you can. And that may be the same logic for the snake that eats a big fish.
Right.
And they may not know that they can't how big it is until they get partway down.
And
Well,
then
they
the
can
thing
extract-
is, like,
they
could that
regurgitate,
snake
right?
extract
They can-
itself, like, it looked like it's gonna, like, die, like, it looked like it was never gonna make it.
Sometimes they do die. Sometimes they'll try to eat food item. I've seen garter snakes dead from trying to eat sculpins. They're
Yeah,
too,
that's what this
They're
was,
too
it
big.
was the garden
Yeah.
snake open, yeah.
yeah, they get killed sometimes. Snakes get killed by prey that they can't swallow. That happens. Garter snakes feeding on Tarika, on rough-skinned newts. So rough-skinned newts, okay, I'm going to tell you that. I'm going to talk about amphibians, so I'll just start out with the rough-skinned newts, which you guys have to meet. Where's the rough-skinned newt? Let's see, I have a rough-skinned newt. So these guys are one of the most toxic vertebrates known. So don't eat it. It won't, you can handle it, you can just wash your hands, but please don't eat it, because it'll kill you. They have tetrodotoxin. Tetrodotoxin is pufferfish toxin. It's in the skin of rough-skinned newts. They used to call it Tarika. Tarika is the genus. It used to be called Tarika toxin, and then they changed it to tetrodotoxin when they realized it's the same thing that pufferfish have. And that toxin binds to sodium channels, and in your, all your nerves function, your action potentials in your nerves are brought about by sodium passing across the cell membrane, and basically these guys just shut down your nerves instantly in there. It's an incredibly toxic substance.
Is it dangerous to hold them?
No, just don't hold them and stick your fingers in your mouth, and don't eat it. You'll be fine. I've held lots of them. Wash your hands. Don't even, probably better not to pick it up. Just look at it. But I've picked them up, and they're very toxic to predators. So garter snakes love Tarica. And there's, I'll show you, we've got, these will get the garter snakes out already. So let's see. Where's the, put them together. So where's the garter snakes? So we have a couple of species of garter snakes here in our valley. Let's see. I think you see there are two. Is that one? Is that the alligators? Yeah. Well, there's some garter snakes. There's the. So Scott's got these two garter snakes he's going to show you guys, and garter snakes feed on salamanders and frogs and fish. And there's this wonderful example of coevolution between Thamnophis herpetolus, a common garter snake, and these salamanders. And it took people a long time to figure it out, but the garter snakes can eat salamanders. But what they do is they test them. They'll eat, if it's a really big Tarica that's loaded with toxins, the garter snake will eat it halfway, and somehow they sense the toxicity and they will regurgitate it if it's too toxic. And the garter snakes have evolved resistance to the toxins, and they basically have different proteins on the surface of their cell membranes that keeps the tetrodotoxin from clogging the pores across their membranes. It's amazing. And the people who figured this out have figured out, it helps to understand how physiology works, and drugs that can be used to help cell membranes. So I wanted to just give you a little appreciation for the wonder of amphibians, because a lot of what we talk about ectothermy applies to reptiles. So amphibians have this great name, amphibios, 2 lives, or double life. And that has to do with half of the life cycle of amphibians is spent in the water, the eggs and the tadpole phase, whereas a part of the life cycle might be spent on land. Some amphibians are entirely aquatic, and some spend a lot of time on land, like this western toad. But the key feature to appreciate about amphibians is they, unlike reptiles, they have leaky skins. And letting water move across the membranes of the skin is super important for amphibians. That's how they function. It also makes them vulnerable in some ways because they're more in intimate contact with their environment. So the term Lis amphibia is the technical name for the class, which refers to a smooth, scaleless skin. And another resource, Mary, I want to make sure you get this. This amphibia web is really
we'll
good.
have to add that one to the list.
Yeah, it's a great site at Berkeley's for amphibia. It's all around the world. So some of the consequences then of this ability to have part of your life in an aquatic environment and part of your life in a terrestrial phase opens up a whole new realm of life history, natural history. So tadpoles and adults can exploit different niches. And we see this a lot in our Pacific Northwest amphibians. Here's a Pacific giant salamander, and some of them will metamorphose into complete adults in terrestrial phase, or sometimes they'll spend their whole lives in a larval phase, and they can even reproduce in that larval phase. But it sort of opens up more options for them, for niches that they can exploit, an aquatic one or a terrestrial one. So another consequence of having these two phases of a life cycle, larval in the water and adult on the land, is that a very common phenomenon called pedomorphosis occurs, especially in salamanders. And the timing and rate of development can be altered. And we see it, especially in our stream salamanders. And many adults can retain an aquatic phase, aquatic larval characteristics even though they can reproduce. So a lot of if you find a big salamander in a stream, if you're up in the forest, it's probably one of these Dicamptodon, these Pacific giant salamanders, and they will become adults and retain that larval phase. You've probably heard of the oxalotl. There's a lot of really cool examples of this in sound. So here's another native species. Can you grab this guy, tiger salamander? So here's a tiger salamander. This is an ambystoma. These guys are here in the valley, and these are the champions of pedomorphosis. And some of them will look like this, the salamander on the right in that phase, or if the conditions are right, they will metamorphose into a terrestrial adult phase, like this salamander.
What are the right conditions?
And look, well, I don't really know enough about it to answer that question really well, except for some of these species in the Southwest in particular, when water becomes scarce or the pond becomes crowded, they'll secrete thyroxine into the water. Thyroxine will cause them to develop into an adult phase, and then they leave the water. They move off onto the land, and they'll burrow into moist soil or find another place. Tiger salamanders do this.
Do the two phases breed?
Do the two phases interbreed? I'm sure they could.